Hello and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy, and in this video we'll be talking about how to use calculus to maximize functions. Although we'll use functions of multiple variables in game theory, we'll start this video maximizing a function of a single variable, since it's easier to visualize the single variable case than the multivariate case. Here we have a function with a maximum. We can see that the maximum exists, and that there is some corresponding x value at which the maximum occurs. The blue line in this picture is tangent to the function at its maximum point. Importantly, the slope of the blue line is 0. Since the derivative of a function tells us the function's slope, we can use the derivative to determine a function's maximum. We denote the maximum by max x f of x, as shown at the right of the blue line. The blue line in this picture is vertical and intersects the function at its maximum. It represents the other quantity of interest to us, namely the x value where the maximum occurs. We call this special x value the argument of the maximum and denote it argmax x f of x, as shown at the bottom of the blue line. Now let's do a sample problem together. Let f of x equal 20x minus x squared. We'll use calculus to find argmax x f of x, max x f of x, and graph them together with f of x, constructing the picture we saw in the previous 3 slides. First, we'll find argmax x f of x. As we said earlier, the maximum of f occurs where its derivative is equal to 0. So we'll find the argmax by computing the derivative f prime, setting the derivative equal to 0, and solving that equation for x star. We'll use x star to denote the value of argmax, and to distinguish between the value of argmax and other possible x values. Take a moment here to recall your first semester of calculus. I myself am recalling my first semester of calculus. Those fond memories tell us that f prime is 20 minus 2x, so we can find the argmax by writing f prime of x star is equal to 20 minus 2x star is equal to 0, and solving this equation for x star. After a few more algebraic steps, we conclude that x star is equal to 10. Now that we've located the argmax, we can find the maximum of f by evaluating f at its argmax, namely 10. A few algebraic steps later, we conclude that the maximum of f is 100. At this point, we've completed our use of calculus to locate the argmax and max of f. Note that we found the argmax first, since setting the derivative equal to 0 and solving for x tells us the argmax, i.e. where the maximum occurs. Only after this step can we compute the maximum of f. First, graph f of x. The computer renders the graph very nicely here, but oftentimes the early versions of a graph are best made by hand. A good general rule about making graphs by hand is that while they don't have to be works of art, they should be neat and be large enough to make apparent all of the interesting features you want your graph to show. Use a ruler for straight axes and lines, and either use graph paper or a ruler to make sure your scale is reasonably consistent on each axis. In this example, the interesting features we want our graph to show are the argmax and max of f of x. The argmax is 10 and the maximum is 100, so our x-axis should show x values from somewhat below 10 to somewhat above 10, and our y-axis should show values corresponding to whatever we picked for our x-axis, up to something slightly more than 100. Now we can add a vertical line at x equals 10, the argmax. Finally, we can add a horizontal line at y equals 100, tangent to f of x at x is equal to 10. And that's it! Now we'll consider the multivariate case. As we study game theory, each variable will typically represent the action or strategy of a single player. Since games have multiple players, we will have to do some multivariate maximization. The rest of the video will discuss a multivariate example problem. So here's our problem. We have a profit function belonging to firm 1, which depends on firm 1's own choice of quantity and its lone competitor's, firm 2's choice of quantity. Firm 1 doesn't control firm 2's choice, Q2, but it does want to choose its own quantity, Q1, to maximize its profit. We express that firm 1 can choose Q1, but doesn't control Q2, by asking for the argmax of pi 1 over Q1. We denote that firm 1 chooses Q1 only by writing Q1 as the only subscript under argmax and max. First, we'll find the Q1 that maximizes pi1 of Q1, Q2. Well, we won't graph pi1 because graphing in 3 dimensions is not something we are going to make a habit of. The same method from the single variable case still works. The maximum occurs where the partial derivative of pi1 with respect to Q1 is equal to 0. We take the partial derivative with respect to Q1 because we are looking for the Q1 value that maximizes pi1. We'll compute the partial derivative, set it equal to 0, and solve for Q1 star. Similarly to the single variable case, we'll use Q1 star to denote the value of argmax and to distinguish between the value of the argmax and other possible Q1 values. This derivative requires somewhat more explanation than the single variable example from the beginning of this video. First, we have 2 letters in our function, namely Q1 and Q2. Since we are maximizing with respect to Q1, we differentiate with respect to Q1. Since we are differentiating with respect to Q1, we treat Q2 as a constant throughout the problem. Second, observe that pi1 is the product of 2 functions. The first is 30 minus Q1 minus Q2, and the second is Q1. The derivative you see below follows from the product rule, which says that the derivative of a product of 2 functions is the derivative of the first times the second, plus the first times the derivative of the second. If you prefer to distribute the Q1 in pi1 and then differentiate the function, and that does seem to be the common preference, then by all means do so. Both methods are equally valid, so the one you pick comes down to personal preference. You can infer my preference from this example. Now, a few algebraic steps, and we obtain Q1 star is equal to 30 minus Q2 all over 2. Note that we solve for Q1 star in terms of Q2 and not the other way around, since we are looking for the Q1 star that maximizes pi1 for a given Q2. It shouldn't surprise us that our expression for Q1 star depends on Q2. That Q1 star depends on Q2 tells us that firm 1's profit maximizing quantity depends on firm 2's choice of quantity. In other words, firm 1 and firm 2's decisions are strategically interdependent. Now that we've found the argmax of pi1 with respect to Q1, we can find the maximum of pi1 with respect to Q1 by evaluating pi1 at Q1 star. A few algebraic steps later, we conclude that the maximum of pi1 with respect to Q1 is 30 minus Q2 all over 2, all squared. Again, it shouldn't surprise us that Q2 appears in our answer. Its appearance tells us that firm 1's profit depends on firm 2's choice of quantity. It isn't necessary or advisable to multiply this expression out. Multiplying it out introduces opportunities for error, and keeping things factored nicely is often easier for the reader. I know there are some simplest form zealots out there who might differ on what form this expression should take, but fortunately for me, I'm making this video, so my own, possibly zealous opinion will prevail for now. At this point, we've completed our use of calculus to find the argmax and max of pi1 with respect to Q1. We're not making a 3D graph, so we're done. Thanks so much for watching this video about how to use calculus to maximize functions.